Welcome back. In this video, I'm going to show you 3 examples of how we draw organic molecules given the name. And so in this case, we're just going to be looking at simple branched alkanes and haloalkanes. So that is alkanes with halogens attached at various positions. So let's first look at this first example. The best way to do this is just to dive right in. And you guys have already seen me do this in class, so let's go ahead and start. The very first thing we're going to do is identify the parent chain. So in this case, our parent chain is hexane. Now hexane, the prefix 6, tells us that there's 6 carbon atoms. So the very first thing I'm going to do is I'm just going to draw 6 carbons like this. Okay, 4, 5, and 6. Now I'm not putting any hydrogens on them yet. We will eventually have to do that. But now that I've drawn the parent chain, at least the carbons for that, I can now go and identify the different groups. Okay. Now this tells me right here that there's 3 methyl groups. So remember what a methyl group is. A methyl group is where you have a CH3 attached to the chain at some point. So there's 3 of these. And the numbers out in front tell me what positions they're at positions 2, 3, and 4. That is carbons 2, 3, and 4. And the nice thing about going from the name to the structure is I don't have to worry about counting from this side or this side. I can just say this is position 1, 2, 3, 4, 5, and 6. Okay. And so this tells me I have 3 methyl groups. The first one's at position 2, so I'll just draw that one going up. It doesn't actually matter for this purpose right now if you're drawing it up or down. There's another one at position 3. I could draw that up here as well. And then another one at position 4. I'll just draw that down just for reference. And so now that's all the groups added on. I got the 3 branching groups, which are all methyls at positions 2, 3, and 4. The only other thing I really need to do is add in the appropriate number of hydrogens. And I just need to remember that each carbon must have 4 bonds. So this carbon would have to have 3 hydrogens because it already has 1 bond to this carbon over here. Okay. This second one would actually need 1 hydrogen, so just 1, because it has 3 bonds already, 1 up, 1 left, and 1 to the right. This carbon would also need 1 hydrogen because it has already 3 bonds, 1 left, 1 up, 1 right. This one, same thing, 1 hydrogen. When I get over here to number 5, this one will actually need 2 hydrogens because it's already got a bond to carbon going left and 1 to right. And then this terminal one will have 3 hydrogens. Okay. And so whenever I draw this compound, I always need to make sure that I've got the appropriate number of hydrogens on each carbon. And if you have a simple alkane, okay, where there's no halogens, it can be branched, but as long as there's no weird functional groups on it, remember what you can do is this rule, CnH2n plus 2. Okay? This will tell you how many hydrogens it ought to have. So we know there's 6 carbons in the parent chain and then 3 additional carbons that are branches. So n in this case equals 9. That's my number of carbon atoms. So the number of hydrogens ought to be double that plus 2 more. So the number of hydrogens has to be 2 times 9 is 18 plus 2 is 20. And if I wanted to, I could count up these hydrogens and make sure that they add up correctly. So we could do 3, 6, 9, 12, 15, then 16, 17, 18, 19, 20. So sure enough, number of hydrogens are correct, and I promise you this is the correct structure right here of 2,3,4-trimethyl hexane. All right, let's go to the second example. We're going to draw 2-chloro, 3-ethyl octane. So in this case, our parent chain is octane. This tells me that it has to have 8 carbons in a row. So let's go ahead and draw those. We've got carbon, 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 that's 4, 5, 6, 7, 8. And I can even go ahead and put these sort of bonds in right there. All right, so that's 8 carbons. Now, for groups, first of all, it tells me that there's a chloro group on position 2. So we count over 1, 2. So there has to be a chlorine atom right here. So we'll put Cl. Make sure you realize that chlorio or chlorine is not just C, that's carbon, it's Cl. You can look at the periodic table in group 7, the halogens. And then at position 3, there's an ethyl group. Ethyl group looks like this. You have a CH2 and then a CH3. So this particular branch is actually 2 carbons long. And so it'll be CH2, CH3. That's an ethyl group. And it's at position 3, as it tells me in the name. So really the only thing left is just to put all the hydrogens on. That's it. So this terminal one right here, this will have 3 hydrogens. One thing you'll see sometimes is they'll put on the terminal one on the left, they'll put the hydrogens out there. I put it to the right of the carbon on the first example. It really doesn't matter. But this second carbon will only have 1 hydrogen because this carbon already has 3 bonds. One to this one to the left, one to the right, and then one to the chlorine going down. Same thing for this third carbon. It'll have 1 hydrogen because that carbon already had 3 direct bonds. And then pretty much these carbons up to the terminal one will all have 2. Okay. And then the final carbon will have 3 to give every carbon 4 bonds. Now, a couple of notes here. Chlorine, you sort of treat the same way as hydrogen. Okay. You would do the same thing for fluorine, really any of the halogens. Each of those halogens, for our purposes, can only have 1 bond. So you don't need to saturate the chlorine with hydrogens. Okay, that's only for carbon, at least right now. Okay, so this would be my structure here. The only other thing I'm going to mention about this is that this rule where we used in the first example to calculate the number of hydrogens, this no longer works because we have a chlorine now. So actually what we would end up seeing is we'd have 1 less hydrogen for each halogen that we add. So this does not work for haloalkanes. Okay, this one you really just have to verify manually. All right, let's do one more example. We're going to draw the structure of 4-bromo, 2,3-diethyl, 5-methyl-decane. Okay, again, this one's pretty complicated, but again, we're just reading this like we would read a sentence in English. It tells us exactly the ingredients in the recipe that we need. So what's our parent chain? Our parent chain is decane. The dec tells me that it has 10 carbons. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's the decane parent chain. And what else does this tell me? I've got a bunch of different functional groups here. I've got a 4-bromo, so we're going to put a bromine on the position 4. So 1, 2, 3, 4. Go ahead and put a bromine. We'll put it up this time. Doesn't really matter for our purposes right now. We have 2 ethyl groups. Again, it's 2 because I have this di in front of the ethyl. So diethyl, there's 2 of them, and they're at positions 2 and 3. So I'll put this one going up. So CH2, CH3, that whole thing is an ethyl group. There's another one at the 3 position, so 1, 2, 3. I'll put this one going down just to save some space up top. So another ethyl group right there, CH2, CH3. That takes care of those. Then we have a methyl group at the 5 position. So 1, 2, 3, 4, 5. Notice you're also having to count from the same start point every time you do this. I wouldn't start all of a sudden counting 1 over here. So here's position 5. I have a methyl group. That's just a CH3. And that effectively adds all my functional groups on there, all my branches. So now the last step is just adding the appropriate number of hydrogens. And again, because I have a halogen in there, this rule of CnH2n plus 2 does not work. Okay, so this would have 3. This one would have 1. This one is 1 as well. 1 there, 1 there. Remember, I'm just giving every single one of these carbons 4 bonds. That is the requirement. We talked about that extensively in class. This one is also 2, and then my last one, terminal 1, is 3. And so that gives us the structure of 4-bromo, 2,3-diethyl, 5-methyl-decane. So hopefully this process makes sense. Again, pretty much when you're going from the name to the structure, I think this is the easier one to do because, again, this is just like reading a sentence in English. It's like reading a recipe when you're making cookies or pizza or something. It tells you exactly what you need and where you need it and how many. So hopefully this made sense to you. Please make sure to like this video and subscribe to my channel for future videos and notifications.